bottom.
It says record.
Yeah.
And then a little light blinks. It says blinking red. Now it's blinking
Yeah,
red.
for me, it's under more. I could record on this computer, record it, but I should keep my computer as doing as little as possible, because I do have to warn you that I've had a few issues with this restarting for no reason, and I hope that doesn't happen. Let's see.
Right, I guess we can start. So today, Ben Hayes is going to speak about harmonic models and Bernoullicity. I advise everyone to turn off the video, so it makes the recording better.
Even me?
Thank you. No, well, I guess you can keep the video, but the rest should shut it down somehow.
Okay. So should I get started?
Yes, please.
Okay, cool. All right. Well, thanks, Kate and Lewis, for letting me give a virtual talk. Yeah, so it's on harmonic models and Bernoullicity. So this is going to be part of the study of what are called algebraic actions. I'll define what those are in a second, and it's motivated by the problem of trying to understand when certain algebraic actions are Bernoulli shifts, which I'll also define, but probably a lot of people already know. But okay, and I have really 23 slides prepared. It's maybe a bit less than I normally would do for a 15-minute talk, but I don't have to get through all of them anyway. So if you want, please definitely stop me for questions if whatever you feel is appropriate. Okay. So what I'm interested in, one of the things that I have a now basically decade-long obsession with are algebraic actions. This is an action of a countable discrete group G on a compact metrizable group X by continuous automorphisms. Now, if you give X the Haar measure, M sub X, then this is a measure-preserving action. So I didn't say what the Haar measure is here. Again, probably a lot of people know it. But if you don't, it is the unique Borel probability measure on your compact group for which is invariant under the group operation. So if you take the map, if you fix X in X, and you take the map Y maps to XY, then this map preserves the measure, the Haar measure. And there's only one measure which does that, and this is it. So I can think of this as a measure-preserving action, so I can view it from the lens of ergodic theory. You can also view this from the lens of topological dynamics, and that's less important for my talk, but you can also do that. It's important for other things that I do, but for this talk, it's not really relevant. And it connects to a lot of fields. This is one of the reasons it's really exciting, is that it connects to a lot of fields. Functional analysis, that's sort of primarily where I come through. Operator algebras, that's also primarily why I and of course lots of other people come through. Fourier analysis, we'll hopefully get a chance to see that in the talk. Fourier analysis, both on R to the D and Z to the D, and on the compact group X itself or other compact groups. Algebraic geometry, when G is abelian, this will sort of be less relevant for my talk, but it's certainly very interesting, and lots of people in the audience have done fantastic work in this direction. And what is definitely going to be relevant, and again, hopefully I have time to mention details on this, random walks and probability theory. Okay. Maybe before I get into this, I'll sort of indicate this later. Why do we study algebraic actions other than, they connect to a million different fields, and that's always exciting. and it's sort of another, well, there's several reasons. Well, let me say, well, one is there are natural class of actions defined for any group, and we don't really have many of those, like PMP actions defined for every group. There's like algebraic, there's Bernoulli actions, algebraic actions, Gaussian actions, and that's about it. So that's one reason. The other reason is I like to think of it as sort of like a Goldilocks situation. It's tractable enough that one can actually prove pretty general theorems that are interesting, but those theorems are difficult enough to prove that the proofs are like non-trivial and also interesting. So it's a good source of appropriate level difficulty problems. We don't want things to be too easy, otherwise we're not really saying that much significant maybe. But also we don't want things to be so hard that just nothing can ever be said and there's no theory whatsoever. So it's sort of a Goldilocks situation, as I like to say. I'm going to need to talk about one of the main classes of examples that people study a lot. And for this, I'll need to talk about the integral group ring. So I'll take the ring of all formal sums, A, G, G, where A, G is an integer, and the set of non-zero coefficients is finite. So you can do this for any commutative ring. You can replace Z by any commutative ring, and I'll replace them by the real numbers later. You really only need to care for this talk for the integers, rational numbers, real numbers, and complex numbers. Right? Okay, sorry, that was being a little sticky. This is how you define the multiplication. It's convolution if you know that, but really just think of it as you know how to multiply group elements, and you declare that your scalars, the integers in this case, commute past group elements, and you just define addition in sort of the obvious way, and you extend multiplication the only way that extends the group operation and is distributive, and forces integers to commute past group elements. It's also relevant for my talk that you have an involution star. So the star of a sum like this is you just take G to G inverse, and you replace A, and you just fix AG. If Z was the complex numbers, I'd have to throw in a complex conjugate, but everything is sort of real, and that basically will be for this talk that's not really a concern. And the sort of reason for existence of this thing is that if you have an abelian group on which G, your discrete group, acts by automorphisms, then it becomes a module over this non-commutative ring by just sort of the naive thing, like you just apply G to your element A, and then you just sum up with these coefficients. And because I'm in an abelian group, I can multiply any element in that group by an integer. Okay, so this is exactly what I just said. Okay, so this gets a class of examples called principal, and I'm trying to also use this as an opportunity to push around a name for a slightly more general thing, which I'm going to call balanced algebraic actions. So for something in the integral group ring, you can look at the Pontryagin dual of ZG mod ZG times F, right? So ZG times F is a left ideal in ZG. When I mod this out, I no longer get a ring, but I get an abelian group, and it's clearly a ZG module. So this is the group of all additive homomorphisms from ZG mod ZGF to T, and for the purpose of this talk, and this varies from person to person, but for me, T is R mod Z. And of course, that's identified topologically with the circle, so that's a compact group. And I should have mentioned that, okay, so the group of all additive homomorphisms, that's a special collection of maps from ZG mod ZJF to the torus. And so it's a subset of T to the ZG mod ZJF. It's actually a subset of T to the G because of additivity, but at any rate, it's a collection of maps with values in a compact space and domain a discrete space. And so just by the Tikhonov theorem, you can prove that it's closed under the product topology, and so by the Tikhonov theorem, it's compact. So that's a compact group. And you have an action by just shifting the coordinates. If phi if phi is an element of XF, I have to tell you what G phi is. Well, G phi is supposed to be some other element of XF. It's supposed to be some other additive homomorphism from ZG mod ZGF to the circle. Okay, So I have to tell you what G phi's value at A is when A is in ZG mod ZGF, and G phi's value at A is just phi of G inverse A. Okay. So this action is called a principal algebraic action, and this won't be so important for this talk. You can only, if you only care about principal algebraic actions, that's fine for this talk. But for a lot of purposes, you know, almost everything that I've proven in the past, you know, like I said, 10 years or so, for principal algebraic actions works for what I'm trying to start kicking around the name of balanced algebraic actions. So that would be more generally, you take n-fold direct sum of ZG and then you mod out by a square matrix. If you take a non-square matrix, like if you took some k by n matrix over ZG and it took ZG direct sum n mod ZG direct sum k times that k by n matrix, then that would be just all finally presented ZG modules, ones which have finitely many generators and relations. This is balanced because you have the same number of generators as you do relations.
Are you making any assumption on B in this?
No, but assumptions will come later.
Okay.
F will have a very, again, there won't really be a B, that will just be an F actually, but I'm just, you know, using this up as an opportunity to try to set a trend. And also to remind people that this is another situation where we can say a lot of things. There'll be some mild invertibility hypotheses that will be mentioned very shortly. Okay, does that answer your question?
Yep.
Okay, cool. So yeah, like I just said, of surprising significance here are formal inverses of F or B in L1 of G, or n by n matrices over L1, and also L2. And it's hard to say what I mean by L2 because when I say inverse, I'm really talking about an inverse under convolution, and L2 of G is not it's not closed under convolution. So I'll say what I mean in a second, but this turns out, you know, if you make this as an assumption that F has what I'll call a formal inverse in L1 or L2, and I'll be very explicit about what that means later. This tells you a surprising amount of additional information that you can use to get some nice theorems. Okay, so that's what's going to be harmonic models. I should mention it again, especially because some of the people are in the audience. There's lots of work by a lot of people on algebraic actions, particularly in the principal and balance case, and basically any question you would want about ergodicity, about the ergodic theory or the topological dynamics of this action, has been you know, approached in some direction. So whether it's ergodic, is it mixing? What is the entropy? Does it have completely positive entropy? I guess those last two questions, we can really only say anything about when the group is sophic, but you know, Lin, Schmidt, Verbitsky, Bowen, Hanfeng Li, David Kerr, Gaborio, Seward, and you know, I've done some work in this direction too. Okay. So I'm going to mention two particular cases of interest, and then I'm going to, you know, I think all principal algebraic actions are interesting, but I'm going to mention two particular cases of interest, and one is the harmonic model. So this is where you look at an element of the integral group ring, which is of the form some constant times 1 minus p, where this constant is an integer. P is now in the rational group ring, and P can be written as the sum of mu GG with mu a finally supported probability measure. Okay, so you take some finally supported probability measure, use that to get an element of the rational group ring, if that measure has rational masses. Okay, and you look at 1 minus that, and you take a constant times that. So if I just looked at 1 minus this measure, this is something that shows up a lot in geometric group theory, and again in operator algebras and various things. That's a combinatorial Laplacian. It's related to harmonic functions on the group, and so we're taking an integer version of that. I can't take 1 minus p and get an element of ZG because it doesn't have integer coefficients, right? So I have to scale it. Okay, so for example, if you take something in R to the G, it's mu harmonic if and only if xf is 0. Again, here I'm using that I have a right action on R to the G by right shifting coordinates, so I can make, you know, R to the G is another abelian group on which G acts by automorphisms, so I can make sense of xf. It's a right action, but okay. So basically, by definition, it's harmonic, really, if and only if x is xp, but of course that means x times 1 minus p is 0, and I can just throw in this constant. If I take something in r to the g and I look at the quotient map onto t to the g, well, I should have mentioned this before. The Pontryagin dual of zg is t to the g. I'll actually sort of more or less explicitly prove this later. So xf, that's because that's the Pontryagin dual of zg mod zgf. It's some closed g invariant subgroup of t to the g. And again, this will be explicit later. So if you hand me something in r to the g and you ask me, here's its image in t to the g under the quotient map, when is it in xf? That's the same as saying that theta times f star, and I'm really going to be dealing with not symmetric things here, so I'll really have to take f star, annoyingly. If theta times f star is congruent to 0 mod zg, if that theta times f star is an integer valued function. Okay? So you can therefore think of xf, the harmonic model in this case, as sort of circle valued harmonic functions. Originally, that doesn't, mu harmonic functions. Originally, it doesn't make sense because, mu is a measure and it's probability measure, so it doesn't have integer masses, right? But basically, by scaling, I can make sense of, a certain collection of things which are sort of t-valued harmonic functions. And for similar reasons that harmonic functions are related to random walks and probability, the harmonic model is also related to random walks and probability. And this has been previously studied, again, by a lot of people, again, in the audience, Bowen-Lee, Kitchen-Smith, Lynn-Smith, Lynn-Smith-Vervitsky. There are other references here, but all of them have names that are a subset of the names already mentioned. So I felt like I was playing it safe by at least mentioning all the names. But okay, I'm definitely underselling how much this has been studied. There's another class of things that we care about. Well, there's lots of, again, I care about all of them, right? But for particular things that we can study and say interesting things, there's another class of elements that are of interest, and those are what are called the lopsided elements. So we say that f in zg is lopsided if it can be written as some integer m, so that's really m times the identity in the group, but m plus the sum over g not equal to 1 of agg, and of course there have to be finally many not 0 ag there because it's in the integral group ring, and the sum of the absolute values of the ags is less than m. Okay, so if you think of the coefficients as some sort of mass of f, the mass at the identity dominates the mass everywhere else. So that's why it's called lopsided. And the significance of these, as I mentioned before, you can view even the real group ring or the complex group ring as a subset of L1 of G. And L1 of G is a Banach algebra under convolution. And so F has an inverse in the Banach algebra because, if I divide by M here, I'm saying that F over M is 1 plus something of L1 norm less than 1. So you just copy the geometric series. Okay. So I'll need another example. And this definition is basically the point here is that it encapsulates lopsided, harmonic, and also harmonic with signs, if you like. So we say that F is semi-lopsided. This is a terminology I produce, so maybe it's not good. If it's not good, shout at me a better one, and I'm open to suggestions. So we say that F is semi-lopsided if it's as above m plus the sum over g naught 1 agg. And now, instead of saying that the sum of the absolute values is strictly less than m, I just say it's at most. Okay, so it no longer has an inverse in L1 of G a priori, and in certain cases it just flat out does not. I'll talk about that later. So the harmonic model, for instance, corresponds to equality in this inequality, the sum of the absolute values is m, and also that all the coefficients, which aren't the identity, are non-positive. Okay, so that's what the harmonic model is. And I guess also I missed here, one of the coefficients should be, m should be positive. Right, so this encapsulates both harmonic and lopsided. Okay, and so what we're interested in here are like I said, Bernoullicity, these actions. So that's the main problem of interest. So now I have to tell you what a Bernoulli shift is. And again, most of you already know this, but okay, just to make sure everybody's on the same page. If you take a countable discrete group G and a probability space, a base probability space omega mu, typically omega is a finite set, but it doesn't have to be. I can take the G-fold power of omega mu. And so what is omega to the G? It's all functions on G with values in omega. So I have an action of G on omega to the G by saying, well, Gx. So if I take x and omega to the G, it's some function on G with values in omega. So what is Gx? Well, it's some other function on G with values in omega. And I have to tell you, in order to tell you what that function is, you have to hand me a group element H, and I have to tell you what Gx's value at H is. So just x of G inverse H. Okay, so this is the same definition we had before for algebraic actions. This is the same definition for the left regular representation. This is, if you study what I study, you think about this every day, right? So this is called a Bernoulli shift. Okay. Bernoulli shifts are I should say one of, but I would say Bernoulli shifts are the most natural example of an action of an arbitrary group. Again, it's a class of actions that are defined for every group. We don't have a lot of those. They're basically, like I said, Bernoulli shifts, algebraic actions, and Gaussian actions. And they're the most natural example. I mean, it's basically, this is like the ergodic theory version of a group acting on itself, right? Basically, you take a group acting on itself, which, in group theory, this is what you think about all the time, and you turn that into a PMP system. The Bernoulli shift is what you get, or the Bernoulli shifts really are what you get. And so, for instance, this is a fact I think I mentioned several times in the talk because it's so fantastic that it's true. If it's sophic, then they can be classified by entropy completely. Just compute the entropy, and that tells you what Bernoulli shift is isomorphic to. I mentioned this later, but that's due to Bowen, Kerr-Lee, and then some very important recent work of Seward. But in general, even if you don't care about classification, you just want to know properties about them, there's so much is known, right? You can say that they're mixing, what the Koopman representation is, most things about PMP systems, if you can say them about anything, you can say them about Bernoulli shifts, right? So they're sort of the first case you try to understand for anything. And so because we know so much about them, and because if they're sophic, which is again, I don't really need what a sophic group is for this talk, but just think a very large class of groups, which is larger than amenable groups, significantly larger, we can classify them. So it's very natural. We have this class of actions we can completely classify to say, if I hand you an action, is it Bernoulli? Is that a tractable question? And certainly it's a question we want to answer. And so for amenable groups, there's a theory that develops this. It's not easy to apply in most cases, but you can apply it in a lot of cases. There are a lot of actions you can say for actions of amenable groups are Bernoulli, and these all use Ornstein theory. So this is developed by Ornstein in the integer or maybe z to the d case, but I believe the integers, but I'm willing to be corrected on that, and Ornstein-Weiss in the amenable case. And it gives you a collection of conditions that if you can verify, prove the action is Bernoulli. Those conditions aren't always easy to verify, but they're, tractable enough that it can be done and in very interesting cases. Like I said, they're completely classified by entropy in the amenable case. And so, we have a relatively satisfactory theory of, you hand me an action, I sort of do some stuff, fuss around for a bit, figure out if it's Bernoulli, and then once it's Bernoulli, I compute its entropy and I say it's this Bernoulli shift, right? So, and that's pretty great. For non-immutable SOFA groups, again, Bernoulli shifts are completely classified by entropy. I guess this slide is slightly a lie. One direction of this, the fact that if two things have the same base entropy, then they're isomorphic. They give rise to isomorphic Bernoulli shifts. That was proved by Lewis Bowen, and then an important step was recently closed. Lewis Bowen didn't handle all the cases, but he handled 95%, and then but the last 5% was non-trivial, and that was closed by Brandon Seward. And for SOFA groups, you use the entropy defined by Lewis and David Kerr and Han Feng. But there's no current version of Ornstein theory, right? If you hand me an arbitrary action, I can't, there's nothing like finally determined, all these conditions that show up in Ornstein theory to guarantee that some action is Bernoulli, we don't have anything like that. And part of the reason for this is that the proofs of the various Ornstein isomorphism theorems are a little opaque. And so, seeing how you can modify them to the non-immutable case. I mean, let me say that a lot of very, very good people in the subject who are I know are in the audience have thought a lot about this and have currently, maybe they're not, maybe they're hiding something, but currently have not, to my knowledge, emerged victorious. So it's certainly a hard problem. Okay, so that's one problem. But there are other problems, other difficulties in non-amenability land. One is that for amenable groups, if you take a factor action of a Bernoulli shift action, and if it's a free action, if for every group element that's not the identity, the measure of fixed points of that element is 0, then automatically it's a Bernoulli shift, and this is just you quote something in Ornstein theory that it says it satisfies one of these conditions and has to be a Bernoulli. This is just not true for non-amenable groups, and this is one of the difficulties you run into when you try to develop Ornstein theory for non-amenable groups. This is one of the difficulties you run into when you try to do anything in the subject, is that factors of Bernoulli shifts in the non-immutable case can be surprisingly complicated. For instance, the result of strained Popa is that if you take this is an algebraic action, right? You take t to the g, and t sits inside there as the constant functions, right? T to the g is functions in g with values in the circle, and you have the constant functions, right? So that's a subgroup, and it's g invariant. If you mod out by it, you get another algebraic action, and it's not a Bernoulli shift of g as property t. Popa actually did this for something much more general than property t, but for the purposes of this talk, let me just say if that's property t. So for instance, if it's SLNZ with n at least 3.
Can you just quickly say why it's not Bernoulli?
Why it's not Bernoulli? Well, depends on what you mean by say and quickly. If you want me to give the full details, no. But the rough idea is that you can compute the cohomology of this action with values, I believe, in the circle, and property t forces that to be much, much smaller than you would expect. And so it doesn't have the same cohomology as a Bernoulli shift, so it's not a Bernoulli shift. Thanks. Yeah, and this is, basically property t implies some rigidity on cohomology, and that is a often running theme in the subject. So it's not entirely out of nowhere. The proof is phrased entirely in terms of von Neumann algebraic language, although I think, and unfortunately I'm now getting myself into trouble, that I think people even in the audience, and I should know their names, and I apologize for not off the top of my head, have translated that to not use von Neumann algebras. Yeah, so sorry if you're one of those people and I am insufficiently prepared to say who you are, but okay. But this is related to, in the entropy theory land, there are lower level versions of Popa's result having to do with sort of connectedness in model spaces and things like that by Tim Austin and recent work of Damian and Bowen. Okay, so factors of Bernoulli shift are not necessarily Bernoulli, but it's important, especially these days, to try to counter blessings as much as possible. Being a factor of a Bernoulli shift does tell you a lot about the action. Okay, so even if it doesn't tell you it's Bernoulli, it tells you quite a lot. It's mixing, has countable Lebesgue spectrum. The spectral gap, if the group is not amenable, it's what's called solidly ergodic. I don't want to get into what that is, but that's some very cool, cool property of the corresponding orbit equivalence relation. If the group is sophic, it has completely positive entropy. That's a result of David Kerr's, and lots of other things. All right, so you still know quite a lot about this action. So suppose we take an algebraic action. One is a Bernoulli. Okay, if the group is amenable, this is the same as asking when is it a factor of Bernoulli, if the action is free, which I'm sort of ignoring in this talk. But if it's not amenable, you know, maybe it's a factor of Bernoulli and not Bernoulli, but it's still interesting to ask, is it a factor of a Bernoulli? Okay, and again, we don't have Ornstein theory, so it's hard to say much. But probably the main really general results on Bernoullicity that's so far known is the following. An algebraic action of z to the d is Bernoulli if and only if it has completely positive entropy. So this is completely positive entropy, for those of you who know what entropy means, just means that every non-trivial factor has positive entropy. I won't get into the definition of entropy in this talk, although I will reference it a few times. But that's a pretty satisfactory answer. And actually, if you know that X is the dual of a certain ZG module, which it always is, but if you know what that ZG module is, and if that ZG module is, say, finally presented, you can relatively reasonably detect if this is true. I mean, there's module theoretic tricks you can do that tell you when this is true. And so it's not a bad criterion. So mention this, this preceded should be succeeded, sorry. This succeeded word of Katz-Nelson and Lind on Bernoullicity of ergodic Tor automorphisms, probably lots of other things leading up to that I forgot. And the proof of this theorem and the theorems just mentioned are not easy. Okay, again, you rely on Ornstein theory, which gets you somewhere to begin with, but it doesn't save the day. It's still quite a bit of work to do this, but okay, it's a very nice result. Getting more specific, for non-amenable groups, basically, the things that we know that are Bernoulli that aren't just sort of obviously Bernoulli, is this recent result of Doug and Klaus, which is that if you take 3 minus x minus y for the group being the free group generated by two letters x and y, then the principal algebraic action is Bernoulli. And this is about all we know so far about, as far as things are being literally Bernoulli, and even more or less even being factors of Bernoulli, aside from things that are sort of obviously so, we don't really have many examples until you get to mine, and that's what I'm going to transition to now. Okay. Maybe now is a good time to pause to get to questions, because I'm about to get to my main result and main. I don't know if I'll have time for my main methods. This is going slower than I expected, but we'll see.
Does the Rudolph-Schmidt result apply for an arbitrary countable abelian group?
Doug would know that better than me. I think so. You might need torsion-free, but as far as I know, it's just z to the d. But it might be tractable for a countable abelian group. Maybe if it's torsion-free.
I think the proof really depends on ZD.
Okay.
And it's pretty tough. You have to prove a kind of asymptotic independence of blocks. And that proof is tough, very tough. And I don't know whether this remains true for an arbitrary, say, torsion-free abelian, torsion-free amenable group, for example.
Okay. Yeah. All right. So now we're going to get to, right. The argument of Lind and Schmidt crucially used the existence of an L1 inverse for F. And this action does not have an obvious Bernoulli partition. They prove it's Bernoulli, but I can't just sort of hand you a clear partition whose translates are independent. Okay, so now I have to get to my results, and so I need some preliminary definitions. We say that a group is left orderable if there is that should be a total order, not a partial order, but a total order on G which is invariant under left multiplication, X less than Y implies that GX is less than GY for every group element G. If G is bigger than 1, we say that G is positive. I'll mention this, hopefully I'll have time later in the talk to say that there are lots and lots of examples of such groups, and particularly, there are uncountably many up to isomorphism in the non-amenable case, for instance. So if G is bigger than 1, we say that G is positive. So a pair G less than, where less than is a left invariant order in G, we'll call this a left ordered group. Left orderable just means that there's some order, and I'm calling this left ordered if you fix that order. Okay. For a finite subset of G, and for me, it's going to be important that this finite subset is not symmetric. And an integer at least 0 will let BRS be S union 1 union S inverse to the R. This is just the ball of radius R centered at the identity in the Cayley graph corresponding to S. S may not generate G, so that Cayley graph might not be connected, but it's still a thing. So the main results I have, okay, so at least get to that, is the following. Take a left ordered group and assume that S is a set of positive elements, right? So it should be all of these, in this order, all of these things should be strictly bigger than 1. Suppose that the ball in the Cayley graph corresponding to S inverse S grows at least like some constant times R to the D, where this constant is positive and D is at least 5. Okay, that's actually a pretty mild restriction. Like, any group you write down that's not virtually nilpotent satisfies this, but even if it is virtually nilpotent, as long as its growth is fast enough, that's true. Take a lopsided element, so exactly of the type that I was talking about before, a semi-lopsided element. Take a semi-lopsided element. Then it's a factor of a Bernoulli shift. If G is assumed amenable, then it's actually isomorphic to a Bernoulli shift with entropy log m, and it actually has entropy log m whenever the group is sulfic, okay? So if you know it's a Bernoulli shift, you know what Bernoulli shift it is, but if it's amenable, I can just quote Ornstein theory to say it's a Bernoulli shift. Okay, so this gets you lots and lots of examples. In the amenable case, it gets you lots and lots of examples of algebraic actions which are Bernoulli, and in the non-amenable case, it gets you lots and lots of examples of algebraic actions which are factors of Bernoulli. And I kind of like to think of this as like it's sort of like the Eisenstein criterion when you learn like Galois theory or something like that. It's not like you hand me an element in ZG and it's going to be of this form, but if I want to produce lots of interesting examples of algebraic actions which are factors of Bernoulli shift, it gives you a machine to do that, just like the Eisenstein criterion gives you ways to produce lots of irreducible polynomials or something like that.
So this applies to 2 minus x minus y in the free group.
Yes, it's a factor of a Bernoulli shift. I don't know if it is a Bernoulli shift, but it's a factor of a Bernoulli shift.
Great.
Yeah. And it applies to 3 minus x minus y minus z in the free group on 3 elements. And there it's an equal entropy factor of a Bernoulli shift. Okay. If it's lopsided, then I don't need this hypothesis on growth, and I just need that it's left ordered, and that it's a set of positive elements. And there are lots of examples of left orderable groups: Heisenberg groups, free groups, Thompson groups, certain mapping class groups, Baum-Slug-Salter groups, the Grieger-Trepp group, braid groups. By work of Hyde and Loda, very recent work in the past few years, I think last year actually, there are continuum many finally generated, simple, non-amenable, pairwise non-isomorphic left orderable groups. And there was sort of related work before that, which I think didn't get you finally generated, of Kim, Koberta, and Loda. Okay. And for such groups, we get many examples of algebraic actions that are factors of Bernoulli. And if the group is amenable, as many of the ones listed above are, I get actual Bernoulli actions. And I sort of alluded to this before, I don't actually need a total order. I can work with partial orders provided the elements in this generating set are strictly larger than 1, and the partial order is G invariant. But for the purpose of this talk, I will just focus on actual invariant total orders. Okay, so before I get into at least whatever details I can in the remaining time on the semi-lopsided case, let me mention the proof in the lopsided case. So take a lopsided element whose support away from the identity consists of positive elements. take the L1 inverse of F. So that is, again, you just define this by the geometric series, and that's geometric series converges because it's lopsided. Okay, I guess there should be a 1 over m inside the parentheses here. My bad. If I take something in minus mm to the g for some real number, for some positive real number m, then x plus zg is in xf if and only if x times f star is in z to the g. But I have this inverse lying around, so I can just convolve with it instead. And this is the same as saying that x is in minus m to m to the g, convolve with psi star for some positive integer m. Conversely, if I take a positive integer m and I look at minus m to m and I raise it to the g power, and those are all functions on g, so I can, and they're L infinity, so I can convolve them by psi star, I end up with things that if you then apply the quotient map, land back at xf. So I have this way to go back and forth from elements in a Bernoulli shift to xf. So the natural thing is to look at the map I get on 1 to m to the g to xf by right convolving with psi star and then adding z to the g. And hopefully I'll have time to get into the details of this, but it turns out that left orderability, the fact that I had positive elements which were strictly larger than 1 in this left order, will show you that when I push forward the g power of the uniform measure on 1 through m, under this map, I get the Haar measure. And that means, by definition, it's a factor of a Bernoulli shift, right? And this is the same method as the Lynch-Schmidt approach. They do, more work in their specific example and prove that this map is actually injective mod null sets, right? As far as that, the part of their proof, which is recovering that this is a factor map, that this pushes forward the Bernoulli measure onto the Haar measure, we recover that. Okay. All right. What about semi-lopsided? I said I can handle semi-lopsided elements, and I'll only describe the case of the harmonic model. First, because it's the most interesting, and second, because it's actually surprisingly the most difficult. So for the remainder of the talk, fix a harmonic model. So F is M minus the sum ASS, where S is a set of positive elements. AS is positive for every S and S. The sum of ASS is M. And I have this probability measure on G, which is the indicator function of S applied to G times AG over M. Now, for the harmonic model, part of the difficulty is that a harmonic model will never have an L1 inverse. Never. Absolutely never. And why is that? If you sum the coefficients of group elements, you get 0. I think everybody sees that. But the map on L1 of G to the complex numbers given by summing the coefficients is a homomorphism, right? So something that it's a homomorphism if you make L1 of G a Banach algebra on a convolution. That's an exercise. And so something which sums to 0 will never have an inverse in L1 of G. Okay. So what ends up being the replacement for having an L1 inverse is an L2 formal inverse. And there should be no hyphen here. It should be L2 formal inverse. We say that alpha in RG has an L2 formal inverse if there is a real valued L2 function. It actually has to necessarily be real valued. I don't want to get into that, but you can prove, even if you allow it a priori to be complex valued, you can prove it has to be real valued. So that alpha times psi is the Dirac mass of the identity. Again, here I'm using that I can view L2 of G with values in R as an RG module because I have the left regular representation, which allows me to shift coordinates. And then, of course, it's a real vector space. This ends up implying lots of things. It ends up implying that, first of all, such a psi must be unique. Psi times alpha is also the Dirac mass of the identity. That's not obvious, but that ends up also being true. So there's no issue with left or right here. It's a nice notion. It's just that it's kind of odd because L2 is not, it's not closed under convolution. So this is not an inverse in the ring theoretic sense. Let me give you an example for the harmonic model. So take a symmetric, finally supported probability measure on the group. Look at 1 minus, on the group, but which has no mass at 1. Look at 1 minus the sum of g not equal to 1 of nu of g times g. Then this element, because nu is finally supported, it's an element in Rg, and it has an L2 formal inverse if and only if, and this is an exercise, you can just directly prove this, if and only if the sum over n of nu convolved with itself n times applied to 1 times n is finite. So if you look at the random walk corresponding to nu, so you start at the identity, and at every stage you choose a point in G with probability, distributed according to nu, and then you move by multiplying to the right that element. So that's a random walk on G. Nu convolved with itself n times at 1 is the probability that xn is 1. Again, that is an exercise. So by a theorem of Bernoulli, if S is the support of nu, and if the ball of radius r in the K-graph of S grows at least like a constant times r to the d, then nu convolved with itself n times is at most some constant times n to the minus d over 2. So the upshot is if n is at least 5, and that's in the symmetric case, and if and only if n is at least 5, then A is above has an L2 formal inverse. Okay, so this explains the n at least 5. Oh, sorry, this should be if D is at least 5. This explains the D at least 5 in our assumption on the theorem. What about an R setting? Remember, this only applied when nu is symmetric, when nu of G was nu of G inverse. In our case, mu is definitely not symmetric because it's supported on positive elements, and if you take a positive element and you look at its inverse, it's less than 1. It's definitely not positive. Right? So it's very opposite of symmetric. I still want to look at the sum over G and G of mu GG, and there's a little proposition here, which is that if 1 minus x star x has an L2 formal inverse, then so does 1 minus x. So instead of looking at mu, I can look at mu star convolved with mu. And I could just run the Bernoulli theorem. And so what I get is if I look at the support of mu, if the ball of radius r and the Cayley graph corresponding to S inverse S, because S inverse S is the support of mu star mu, if that's at least some constant times r to the 5th, then F has an L2 formal inverse. For the L1 inverse case, okay, so now I've shown that in our setting we have an L2 formal inverse, but there's still a problem. For an L1 inverse case, we use that we could convolve an L infinity function on the group by an L1 function. Why convolve, if Y is L infinity on G and phi is L1, then Y convolved with phi is a well-defined thing. It's not true if phi is L2. I can't convolve an L infinity thing on G with an L2 thing on G. It's total nonsense. It doesn't even make sense as a function, right? So how do I do this? We have to find a measurable extension of the convolution map, right? So the convolution map defined before, take an element in G with values in 1 through m, take a function on G with values in 1 through m, convolve with the adjoint of the L1 thing, and then take the quotient map. I have to find a measurable extension of this. And that takes in some input, and one thing it takes in some input is a probability measure on Z. So I want to have a probability measure on Z. I want it to be mean 0, which means that it should have finite first moment. The integral of its absolute value should be finite. And the integral of x against it should be 0. And so for psi in L1 of G, I'll define this static psi as before, right convolve with psi star, and then take the quotient map down to Z to the G. And I want to find some extension of this. So I want to put all such maps, these maps from Z to the G to T to the G, I want to put them in some topological space so I can take limits. That's how I'm going to get my sort of measurable extension. So I'm going to let measure Z to the G, comma nu to the G with values in T to the G be the space of T to the G valued measurable functions on Z to the G. I'll identify 2 such maps if they're equal nu to the G almost everywhere. And I'm going to give this I have to take limits of the L1 case, so I have to give this a topology. So I give this a topology of convergence and measure. So a basic neighborhood of a T to the G valued measurable map are the T to the G valued measurable maps, so that the probability that they're epsilon close to your original map, the nu to the G probability, is bigger than 1 minus epsilon. And that's for some compatible metric rho on T to the G. That's what this rho is. It's just some compatible metric on T to the G. Because T to the G is compact, it doesn't matter what metric you choose. So, I'm getting sort of close to the end of my time, so maybe let me just state the next few propositions and go from there. The first, if you take something with mean 0 on Z, probability measure on Z with finite second moment, then this convolution map a priori defined on L1 has a unique norm to convergence and measure topology continuous extension to a map from L2 of G with values in R to measurable functions on Z to the G with values in T to the G. So it's only defined nu to the G almost everywhere, right? But it has a measure topology continuous extension. Further, it's almost surely G equivariant, right? So for almost every point, the equivariant, and for every G and G, the equivariance formula is satisfied. It's almost surely a homomorphism. And all right, I have an additive structure on measurable functions on Z to the G with values in T to the G. I can add them, and it's a homomorphism if I take psi and I map to thetic psi. This can be a generalization thought of as group generalization of Kolmogorof's three series theorem. In the interest of time, let me not say what that means and just say a few last things, which is that the upshot here is, and people are dropping off like flies, so I'll say that if you take the appropriate nu, which depends, unfortunately, on whether or not the coefficient of the identity is even or odd, if you take the appropriate nu to the G and you push forward onto this map, you do get the Haar measure on XF. So you've directly showed that this principal algebraic action is a factor of a Bernoulli shift. There's a lot of questions which are in the last few slides. Maybe because I'm already over time, let me just not get to that. And just mention one of them, which is that you'll notice, I maybe mentioned this before, the entropy of the action on XF is always log M. And if you look at the nu that I choose above, if M is odd, that's an equal entropy factor map. And it turns out that if M is even, and instead of having a harmonic model, I have a lopsided element, I don't need mean 0, so I can also get an equal entropy factor map. It's very possible that in those cases, this factor map that I produce is actually injective mod null sets, and so this action is actually Bernoulli. But that's my main theorem. There's a lot that goes into it, so maybe let me just stop here.
Okay, thanks. Thanks, Ben, for a very interesting talk. So I'll open it up for questions. You can either post your question on the chat, or you could unmute yourself and ask your question.
And I can also, like I said, I can also write on OneNote if people want something that isn't directly answered on the slides.
So I've got a couple of questions.
Yeah.
The first is in ZD, or in like the Heisenberg group, one thing Evgeny and Klaus and I did was take like a harmonic thing, yeah, and multiply it by a polynomial to make it so that you could invert. In other words, you killed off the singularity. Mm-hmm. That, and that actually works even in a non-commutative setting of the Heisenberg group. There are examples of cases where you take a harmonic thing and multiply it and kind of accelerate the convergence enough to get a summable inverse. And right. I'm wondering if that could possibly work like in the free group.
Yeah, you've asked me this before, and I should actually sit down and think about it. I suspect that for the free group, this might just be not possible. Or at the very least, I suspect that for some non-amenable groups, you really have to use L2 formal inverses here. Yeah, and I think, yeah, my guess is that if you want to do things in the completely general setting, you really need to use this L2 formal inverse. I didn't get into why this pushes forward the Bernoulli measure to the Haar measure. That uses a lot of, that the group is left orderable pretty heavily. Although not so heavily that I think that's really necessary. I just couldn't see how to do it otherwise.
So Ben, what I'm going to do, I have to go because I have to teach soon. I'm going to make you the host.
Okay.
And that way you can continue for, whenever you want. You're in charge.
Okay.
Okay. So great. Thank you for a very interesting talk again.
Thanks.